I think the number almost was something.
Well, I figured
When you these one,
Spring break math is
how much
unfortunately
money
over.
you can work? The parent.
How many people got sick?
$2 grand.
I believe it.
So do.
I know I'm feeling it.
So do we-
Somebody,
Oh, that's what I did.
somebody else in here who is
Yeah.
not going to be here
Yeah.
today, I know is also sick. I don't know what came through in the beginning of March, but it has not been good.
So I don't know.
So if you did not raise your hand, you might want to cover your mouth.
So you got 7.48.
So we're going to finish talking about our gases. Then we're going to, so this is still the lecture 8, I think it's lecture 8 slides. So we'll finish these and then we'll move on to lecture 9, which is very short. And those are just looking at the solids and liquids. So we said gases have a big long lecture on their own because they do so many different things. They expand, they contract, there's pressure, there's volume, there's all kinds of things that we can change. And solids and liquids don't do a whole lot. 2 weeks ago, we looked at the first 2 gas laws. We had Boyle's law, which was the relationship between volume and what? Pressure. And then we had Charles' law, which was relationship between what and what?
Temperature goes down, volume goes down.
Volume and temperature, right? And so we have pressure and volume. And if volume goes up, where does pressure go?
It goes down.
It goes down. Volume and pressure go in opposite directions. What about volume and temperature? The temperature goes up, what happens to volume?
So it goes up.
It goes up at the same time. So remember, if you something you've done probably quite often, if you heat something that has gas in it, it expands, right? Those are the main ideas you need to get from that. Volume and pressure go in opposite directions, and we did some math with that. We'll come back to it again. Volume and temperature go in the same direction, okay? Those are the 2 ideas you need to take from that. We have some other variables that we have to take into account. So, the next thing we're going to talk about is volume and the amount of gas. Logically. Don't even think about it in terms of chemistry or math. If I have more of a gas, is it going to have a larger or smaller volume?
Larger.
Larger volume, right? Don't overthink that. If you have more of a gas, it's going to be bigger. So that's what this is telling us. This is Avogadro's law. Volume is our little squiggly is proportional to N. N is the number of moles. Okay? From here on out, we're going to denote moles in our gas laws with a lowercase n. Okay? We're going to see it a couple different times. It's going to be two or three different laws. So this is saying, as you increase the number of moles, meaning you increase the amount of gas that you have, the number of molecules of gas that you have, your volume is going to go up. If you decrease the amount of gas you have, the volume is going to go down. So mathematically, what that means is that they go in the same direction. And so when you take that into consideration and you write the equation, we get that equation. So that looks almost identical to the volume and temperature one, right? Because we said volume and temperature go in the same direction. If you heat something, temperature goes up, volume goes up with it. Here, they go in the same direction also. So it's V1 over N1 equals V2 over N2. And just like our other laws, it's directly proportional. If you double N, you double volume. If you cut N in half, you will cut V in half. So it's a perfectly linear relationship, which makes the math really easy. Again, I've already rearranged the equations for you. If that helps you, great. but you need to be able to rearrange them yourself on the quiz or the final. Let me just tell you how this law looks on here. On here it is V1 over V2 equals N1 over N2. It's the same equation. What you would do, you would say, I'm dealing with volume and number of moles. So which equation listed here shows me volume and number of moles? And it's Avogadro's. So you would just pick that one because those are the variables that you were given. So that's the equation you need to use. A lot of times when we talk about the number of moles of a gas, we're going to relate it to the volume. And we have to define a number here. Avogadro's law is actually the fact that one of our ideal gases, meaning in a perfect world, a gas is something called STP, and we'll come back to what STP is, has a volume of 22.414 liters. 1 mole of gas has a volume of 22.4 liters. Okay? That's a number you're going to need to know, but I believe it is on here. Yes. At the very top of your cheat sheet. Volume of 1 mole of any gas at STP, 22.4 liters. So you don't need to memorize that number. You need to know what it means. Okay? So we'll have examples here. So this is saying 1 mole of any gas. It doesn't matter what gas it is, whether it's oxygen gas, or carbon dioxide gas, or methane gas, or any type of gas. It does not matter. If it is 1 mole, and you're at this STP, you're going to have a volume of 22.4 liters. STP is a certain set of conditions that we'll define. Okay? And so what this is saying is that it doesn't matter what gas you have. All of these equations that we've been talking about, it's a generic gas. It doesn't matter which type of gas you're dealing with. And so at STP, which stands for standard temperature and pressure, 1 mole of any gas is 22.4 liters. Okay? So standard temperature and pressure is 0 degrees Celsius in 1 atmosphere. On your cheat sheet, it says standard pressure, 1 atmosphere, which is equal to 101 kilopascal, which is equal to 760 millimeters of mercury, which is equal to 760 torr. Then also says standard temperature is 0 degrees Celsius or 273 Kelvin. Okay? So again, you don't have to memorize the actual value of STP. What this allows us to do is to create a reference point and say, this is where we are comparing all of these other measurements to. At STP, all of these things are true. At STP, 1 mole of any gas takes up 22.4 liters. Okay? And so they sort of just picked nice numbers. 0 Celsius in 1 atmosphere. 1 atmosphere is basically what we are normally in. And 0 Celsius is 0. So they picked that, and then experimentally they figured out how much volume 1 mole of gas takes up. So, if you have 1 mole of gas at STP, and it is 22.4 liters, if you increase the temperature, you're going to have more or less than 22.4 liters? More. Increase the temperature, volume goes up. So we're going to use Avogadro's law. We have a balloon, and it contains 0.35 moles of a gas, and it's 8.2 liters. We're going to add more gas to it so that there is a total of 1.2 moles. It says if we keep temperature and pressure the same, what will be the new volume? So we've got our equation right here. We might have to be given 3 of these variables, and we're solving for the 4th. Which one is the one that we need to solve for? V2. So we're starting with 8.2 liter balloon that contains 0.35 moles of gas. And then we're going to end with 1.2 moles of gas, and we'll solve for V2. So V1, 8.2 liters. V2 is what we're looking for. N1 is 0.35. N2 is 1.2. Plug them in. 8.2 divided by V2 equals 0.35 divided by 1.2. So we get 8.2. What does that come up to?
28.
28? Gas law problems are always very good for doing a kind of double check at the end. Okay? Does your answer make sense based on the logic that we know about these gases? Did we increase or decrease the amount of gas that we had? We increased it, right? We went from 0.35 moles to 1.2. So what would you expect the volume to do? Go up or go down? You would expect it to go up. Did it go up?
Yes.
Yes. We started at 8.2 liters and we ended at 28. So you know you at least went in the right direction. So assuming you did the math correctly, you got the right answer. But if you had gotten, say, 1.2, you would immediately know you did something wrong, right? Because you know the volume should go up if you add more gas. So if your calculation says it actually went down, something went wrong. So we can take those gas laws. We get Charles, Boyle's, and now Avogadro's. We can put them together in what we call the combined gas law. And once we have the combined gas law, you actually, if you want, never have to use the individual ones again. Okay? And the combined gas law is also here. It's in here. Okay? So what this is, we take all of the equations and we jam them together. They're just mathematical relationships, so we can do that. And so we have P1, V1, N1, T1, P2, V2, N2, T2. If there's something, one of these variables, pressure, volume, moles, or temperature, that is not changing in the problem, you can just erase it. If you have a problem that has changing volume, moles, and temperature, but pressure doesn't change, erase your P's. And just use that part of it. If you have a question that has changing pressure and temperature, but V and N don't change, erase your V's and your N's, and what you have left is the equation that you need to use. Okay? And so, me personally, I can remember the other individual ones because they make logical sense. So I tend to use the individual ones in problems. If that doesn't work for you, you can just use this. You can use this for any of these gas problems. Okay? Start here, figure out which ones you have, plug them in. If there's N and N here that you didn't have any of them to begin with, just erase it and ignore N. Okay? So this is an example of using that combined gas law. So we have volume, we have temperature, and we have pressure, right? Which variable is not listed up there?
Moles.
Moles. So we are going to completely ignore moles from that equation. So if we go back to that equation and we write it without the ends, we're going to get P1 V1 over T1 equals P2 V2 over T2. And so it looks bigger, but it's not any harder than what you've already been doing. One of these variables has to be missing, and the other ones have to be given to you. Plug them in and solve for the one that you don't have. So let's figure out what they all are. What is P1?
2.75.
80? No.
Wasn't it 2.75?
Yeah.
2.75. The starting pressure is 2.75 atmospheres. What is V1?
The 1.25?
1.25 liters. What is T1?
80 degrees Celsius?
80 degrees Celsius. What is P2?
5 atmosphere.
5.00 atmospheres. That's V2. Well, that's what we're looking for. And what is T2?
185 degrees Celsius.
185 degrees Celsius. Do I just take those numbers and plug them in?
Yes. 12.
Kelvin. Temperatures have to be in Kelvin.
Why do the temperatures need to be in Kelvin?
Celsius does.
Yeah, so we have to convert Celsius to Kelvin. It's because the conversion between Celsius to Kelvin is an addition. Because the conversion is an addition, we have to add 273.15. When we're dealing with fractions, if you add a number at the top and the bottom of the fraction, you change the fraction. If you multiply top and the bottom of a fraction by the same number, you change nothing. But if you add the same number to the top and the bottom, you change the fraction. And so in this case, it doesn't matter what T and V are as long as they're the same on both sides. In these problems, temperature has to be Kelvin. So what is 80 plus 273.15? 353.15 Kelvin. And then what's this one?
Like 458.
458.15. Now can we plug them in?
Yes.
Yes. So we've got 2.75 times 1.25 divided by 353.15 equals 5.00 times V2 divided by 8.15 V2 Everybody get 0.89891?
A92. A92.
Close enough.
Yeah.
I don't know which one's more correct.
Yeah, because A91910. So when you round it, you have to 9 go back to.
Oh, it would have been. Our temperatures are actually better than theirs. They just did
Okay.
458. We have the 458 one.
I got
That's right.
1.8 now.
Mhm. Okay.
That's good. So, we had Bode's law, Charles' law, Avogadro's law. Put them together, and we got our combined gas law. Okay. If you do some math magic, which you don't have to do, don't worry about it. Okay. If you do some math magic, when you rearrange all this stuff together, what you end up with is the fact that P1 V1 over N1 T1 equals a constant. Okay? So that says that if you change one of these four things, the other things are going to change with it to counteract that change. So that mathematically, this combination doesn't change. It stays a constant. So we can take that, and we're going to make one more gas law. All of the problems that we've done so far dealt with changes, correct? We're starting in this situation, we're going to this situation, what is our new measurement going to be? None of those problems was there one point in time saying that if I have this pressure and this volume, what is my temperature? We didn't have any of those. But now we can do that. Now, if we rearrange it again, we get this ideal gas law. It's PV equals nRT. This is on there. This is one of the most, I don't want to say common or popular or classical equations that scientists deal with. PV equals nRT gets burned into the mind of a lot of people, myself included. Okay? So it's on there, but you may not ever have to look it up again if you do your homework. So we have pressure times volume equals moles times this R, which we'll come back to, times temperature. And so R is this constant. So R is just a constant. It is a number that you will always use. And it is on your cheat sheet. It says gas constant, R, and then there's 3 values. And the reason there are 3 values is because there are, in the units of it, there is volume, pressure, moles, and temperature. So it depends on what volume and pressure units you use, the value changes. But we're just going to always use the same one. We're going to use the first one. It's 0.0821. 0.0821, which is that's what I remember. I memorized it as 0.0821, and 0.0821 is what is on your cheat sheet. So when you are using the ideal gas law, for R, you will always just plug in 0.0821. You immediately have one of the variables. For you, it will never be anything other than 0.0821. And that tells you, because you're using the 0.0821, which pressure and volume units you have to use. It's saying that we have to use liters. We have to use atmospheres, and we have to use Kelvin. For the P, the V, and the T in that equation, we have no other options. We cannot use milliliters. We cannot use torrs. We cannot use Celsius. In this case, we have to use liters, atmospheres, and kelvins. But that's not what we have to convert to them. So let's do one of these. What I want you to do is look at this question and see how the wording is different, that it shows you that you're dealing with one point in time and not a change. Okay? Because going forward, you're pretty much only going to have two, if you just use that combined gas law, when you do a gas problem, you either have to use the combined gas law or the ideal gas law. And which one you use depends on whether in the problem anything is changing. So you need to look at that problem and read it and see how this question is written differently than all the other ones we've done. So that you can look at a problem and tell me, is something changing or are we dealing with one point in time? Because that's something that a lot of people are going to ask me later on. Which equation do I use for this problem? And the very first thing I'm going to ask you is anything changing? Once you answer that question, that tells you which equation you need to use. So it says, what mass of oxygen gas will occupy 6 liters at 700 torr at a temperature of 25 degrees? There is no volume 1, volume 2, pressure 1, pressure 2. Nothing is changing, right? We're at one point in time, 6 liters, 700 torr, 25 Celsius, and it says, what mass of gas will give me those readings? That is one point in time. So we had our equation. What was the ideal gas law? What is the equation?
PV
equals nRT.
PV equals nRT. So again, we can only have one missing. If we have more than one missing, we can't do it. So we have to have 4 of those 5. Which one are we missing? We don't have N, right? So that means we have to have all the others. What is P?
6 torps.
700 torr. What is V?
6.0.
6.0 liters. What is R?
That's 0.08.
0821. And what is T?
25 degrees Celsius.
25 degrees Celsius. Which ones do we have to convert the units on?
So pressure and temperature.
We have to convert pressure and temperature. Because we said if we're using the 0.0821, our pressure has to be in atmospheres. And so we're going to 700 divided by 760 is what? 0.921 atmospheres. Then we have to convert our temperature from Celsius to Kelvin.
So 298.
8.15.
8.15 Kelvin. Now we can plug it in. So we've got 0.921 times 6.0 equals N 0.821 298.5.
Two three mole. That's low.
The right number of sig figs? Yes.
That's 2, yes.
Is that the answer to the problem?
No,
No, why not?
it
It's
asks
asking for
mass.
the mass of oxygen.
It asks for mass, right?
Mhm.
But nowhere in any of these equations that we talked about has there been mass, right?
Mhm.
So what we had to do, we had to find the moles, which is in our equation. And now you're all very good at converting from moles to grams, right?
Mhm.
So, well, what is the mass of 0.23 grams of oxygen gas? So we have to
32.
convert that to grams. So 0.23 moles,
1 mole.
oxygen gas,
That's a 32 gram.
32 grams, so 0.23 times 32,
7.4 gram.
7.4 grams of oxygen. that process make sense?
One question is for, you said when we're using the ideal formula and it has the constant, why do we change the torrs into atmosphere? Is it because, oh, okay, the constant?
Because the constant has liters, atmospheres, moles, and Kelvin. If we wanted to use torr instead of atmosphere, we would have to use that one instead. But it's much easier for you to just always use 0.0821 and make sure you're converting your units. We've got another one. We have an oxygen tank, and the tank itself is 2.025 liters. If you're using that oxygen tank, it's going to be, you're going to say it's empty, and you're going to return it to the pharmacy before it is actually empty. Right? There's going to be some in there. It's just not enough for you to actually use. So it's saying when it's empty at room temperature, it has a pressure of 723 torr. It's asking you how many moles of oxygen are actually left in that tank when you return it back to the store. Because you paid for that oxygen, right? You paid for it, and now you're turning it back to them without using it. So how much are you actually giving back to them? So is this a situation where something is changing, or is this a situation where we're at one point in time?
Well, isn't it changing because it's saying when it's empty, it's 29.2? So it wasn't empty initially, right?
Well, it wasn't initially empty, but we're not dealing with when it was full.
Okay.
We're only dealing with it when it's empty. And so it is one point in time. It is as you're handing it back to the person you bought it from. This is the volume, the temperature, and the pressure. What is the number of moles that's in that tank? So which variable are we missing?
Or we're looking for N.
We're looking for N again. So N is missing. So it means you have to have the others. What is our pressure? 723 torr. Volume is what?
2.025.
What is my R?
0.08.
Where's temperature?
29.2.
9.2 Celsius. Which ones do we have to convert?
Or temperature.
Torr and temperature. So convert torr to atmospheres.
0.951.
0.951 atmospheres. Celsius to Kelvin.
302.45 Kelvin.
What exactly do you have to multiply to get to Kelvin again?
You add 273.15.
But with torr you divide by
Divide by 760. So now we've got everything, we can plug them in. We've got 0.95 times 2.025. I'm going to rearrange it now. I'm going to divide these over here. So R is now over here. 0.0821 times 302.35. So basically I get PV or RT.
I've got 0.0776. No.
That,
Mm-hmm.
and this is
No.
moles of,
Oxygen.
make sure you get the same number. Anybody else verify?
I got something different, I got 285, but it might be calculator error.
285?
Yeah.
Do we have to pay attention to the base for this?
Yes.
Oh,
What are they, 0.776?
I got .077,
Yeah.
5 if I round.
You still have it up there? I don't know if it has. Yeah, we have 0.35, they have 0.4. Probably something
But it's actually right.
like that. I would never mark that wrong. I would never mark that wrong. Ours is actually probably better than theirs.
I use .35 and I got a number same with you.
I'm not worried about .001s. Okay. It's slightly different. There's different numbers, and it's asking for mass instead of moles. If somebody wants to come up and do this one, basically the same thing we just did. Just plug in different numbers.
What would be n in this case?
You have to solve for n and then convert n to grams. Well, like we did 2 problems ago. Because you're looking for mass, right? But mass isn't in our equations. Moles are. So if we solve for moles, we can then convert to mass.
But moles are not provided. Okay, question.
Right, but we can. It's the same exact problem again with different numbers. So you'll solve for moles and then convert to grams.
Okay, because what I'm asking is that I remember you had said that we need to have 4 of the 5
Right.
in the equation, but I only see 3.
because the R is the.
Yeah.
Oh, okay, I see.
R is
I
the
see.
one. It's the easy ones to get you. Okay.
I could try if you want.
You will?
Yeah.
Yeah, go for it.
Oh, I just don't.
2-1.
2-1.
I have a question. When I read again, I'm supposed to from here to keep, because if it's not from this is combined factor, so I should keep 3 numbers, right?
It's divided by 760, right?
Right, you get 0.993.
4? Oh, 499.
Temperature, I guess 291.2.
What do you have again?
Oh, to count. 273.1. 291.25. 1.25. as long as the right number of subjects.
Sorry. Is it still oxygen?
Yeah. Third times 32.
Oh,
That's O2. So you get 0.07. And that's moles. Then we multiply by 32 to get grams. Right. Because it says what is mass of oxygen gas remains the same. 32. 32 to 32 grams per mole, and you get 2.46. Good job. Okay. We've got a few more of these thinking, wrap your head around problems. Okay? Again, this is not an optical illusion. The orange balloon and the yellow balloon are the same size. Okay? To me, the orange one looks bigger. I don't know what to you. They look the same to you? We're going to say they're the same size. Whether they are or they aren't. We're going to say they are. This one is filled with CO2 gas. This one is filled with oxygen, O2 gas. And we're going to answer these questions. First one is, which one has the greatest number of gas molecules? Yes, Coach.
They're the same gas molecule
Right. Why?
because they both have O2. Wait, that is not a gas molecule. Oh wait, I was thinking atoms. I thought it was yellow. It's cold.
That's a constant
They're
number.
the same size.
Right.
Or 6.022 times
Right.
10.
All gases behave the same. And so at a certain temperature and pressure, X number of moles of any gas will give you the same volume. And so if you have two balloons that have the same volume, and they're right next to each other, so they're at the same temperature, they're at the same pressure, they have to have the same number of moles in them. In this case, we have a certain number of moles of CO2, and that one we have the same number of moles of O2. If there was a different number of moles here, the volumes would be different. Which, well, okay, that's basically the same question. We'll skip this one. Which balloon has the greatest mass?
I would say the orange, no, orange color.
Why the CO2?
Because you have two pressed together.
Right. Yeah, Cole, you have a question?
I was just gonna say the same.
Yeah. So you have the same number of molecules in both, right? So say there's 12 here and 12 here. These molecules each weigh more than each of these. This is CO2, and this one is just O2. And so each of these weighs more. You got the same number, so this balloon is going to weigh more. Right? Which balloon, this might be the trickiest one, which balloon has the greatest density?
I would say
Cold.
orange color. CO2.
Why CO2?
Because it has a whole other atom to it. For the atomic mass.
Because they both have the same volume, you divide.
Correct, you're both, right. And so the fact that this is CO2 meant that gave it the greatest mass, right? In density, what's the equation for density? Mass over volume. And we said the volumes are the same. So whichever one has the highest mass has the highest density. So even though the different gases have the same number of moles between them, the two balloons have the same number of moles in them, the masses and the densities are different. Just because one is the same doesn't mean everything else has to be the same. So now, the yellow one is definitely smaller than the orange one, okay? So now, are the number of molecules different in the two balloons? But between them, between the two. Is there a different number of molecules in the orange one than in the yellow one?
Yes.
They weigh more.
I thought you said.
Well, I thought you said the
Because they said
same.
they were the same, but they
No,
weigh
I'm
more.
But they're not the same volume.
Now, they're not the same volume.
Oh,
Here, they were the same volume, so they had the same number of moles.
oh, so now.
Now, they're not the same volume.
How do you know something's
The
smaller? Oh,
picture-
because it looks smaller, okay.
It's a tricky, the picture, they're basically right on top of each other and there's a small change. See, good. So the number of molecules is different. Which one has more? CO2. The bigger balloon has more molecules. Which one has more moles, or are they the same? CO2 has more moles. Which one has more mass? CO2, right? It's bigger, there's more moles, and each molecule is heavier. Which one has greater density?
It depends, because the volume's also big.
Right. We can't tell by looking at that, because the mass and the volume are different between them. And so yes, the CO2 has a bigger mass, but it also has a bigger volume. And so you would have to actually have numbers to plug in there. We don't have the numbers to plug in. Okay? Let's go back and imagine this was the other way around. Let's say the yellow one was bigger than the orange one. Which one would have the greater mass?
Still the CO2, because it has an extra element. It's normal.
Isn't it way more?
But only so we've got CO2 and O2.
Are the volumes the same?
No, they're not. The oxygen one is bigger.
So the math is the same because.
This is another one that we can't tell. We can't tell. CO2, the molecules are heavier, but we have more of the oxygen molecules. And so maybe if we have enough of the oxygen molecules that are lighter, they can add up to more of the CO2. And so that is a problem I cannot ask you. It has to be tailor-made this way where there is a specific answer, because CO2 is not only bigger, but it's also heavier. Last gas law is a simple one. It's Dalton's law of partial pressure. This says if you have a sample of gas, and it's a mixture of gases, it has oxygen in it, it has CO2 in it, it has nitrogen in it. Our air is a mixture of gases, right? It says if you take the pressure of the nitrogen, and the pressure of the oxygen, and the pressure of the CO2, and the pressure of everything else in it, and you add them all together, what you get is the total pressure. So the atmospheric pressure that we measure with our barometer is the total pressure of the CO2 pressure, plus the nitrogen pressure, plus the oxygen pressure, plus the methane pressure, plus all of those. What this basically says is that even though they are a mixture, they all behave independently of each other. The oxygen doesn't even know that the nitrogen is there. It has its own pressure. The nitrogen has its own pressure. But we are interacting with both the nitrogen and the oxygen. And we can't tell the pressures apart, and so we see the one combined pressure pushing on us. So, the type of problem that you would see with this is an example. Let me just make one. There is definitely one on the electronic homework for this week. These aren't hard. You just can't. This is not one of those types of questions that you can't overthink it. They're easy. Don't make them hard. Okay. So let's say we have two gases mixed together. We have nitrogen gas and oxygen gas. If the total pressure in our container is 6 atmospheres, and I tell you that the pressure of the nitrogen, we call that the partial pressure, is 2 atmospheres. What is the partial pressure of oxygen? 4. So that plus that has to equal that. So this has to be 4 atmospheres. Okay. Another way to look at this, and I think the way the homework problem is worded, is the pressure comes from the number of molecules that you have, right? And so if I say that there's 6 total atmospheres of pressure, and 2 of them are coming from the nitrogen. 2/6 is a third, right? So that means a third of the molecules, because a third of the pressure is coming from nitrogen, a third of the molecules in there are nitrogen. And so if I told you that there was 6 atmospheres and 2 atmospheres, you can find 4. We did that. If I said that there are 6 total moles of gas in there, the 2 and the 4 are also moles. If something gives you a third of the pressure, it is a third of the moles. If it gives you half the pressure, it is half the moles. If it is 3/4 of the moles, it's going to give you 3/4 of the pressure. Okay? When you get to that problem, if you're struggling with it, email me. Overthinking that one is not going to help you. Okay? Okay. I think this is the last topic for this particular lecture. This is more or less how we've already been describing our gases. Because I used these ideas as we went to help you get an idea of what we're talking about at the time. But now that we're at the end of the gases, we're going to put them all together and use them as this overarching theory of the gases. Okay? This is the kinetic molecular theory, or abbreviated KMT, that explains how we observe gases. Okay? The first postulate of the kinetic molecular theory is that gases are made up of small atoms or molecules that are widely separated. You knew that. Molecules and atoms are small, and if you're in a gas phase, you're way apart. That's not big news to you. So that's number one. But this helps explain why CO2 gas in that balloon took up the same amount of volume as the same number of moles of the oxygen gas. It's because almost everything in there is empty space. Imagine if you were making, in the lab when you use these kits, and you made a CO2 molecule. That CO2 molecule is actually going to be a little bit bigger than an O2 molecule, right? And so theoretically, a mole of CO2 should take up more space than a mole of O2, because the molecules themselves are actually bigger. But the molecules themselves take up less than 0.1% of the volume of a gas. And so the difference in the size of the molecules is completely negligible. You don't even worry about it. Because what really makes up the space in that balloon is empty space. and CO2 and oxygen will have the same amount of empty space. This also explains why gases have low densities. If most of what you have is empty space, you have a lot of volume and very little mass. So you get a very low density. Also explains why gases can easily be compressed. If you have a lot of empty space, it's easy to take your gas and push it together. If you don't have a lot of empty space, when you do that, the molecules start hitting and pushing back. Second postulate is that all of the particles behave independently of each other. If you have a sample of CO2, the CO2 molecule over here doesn't care about the CO2 molecule over here. It flies around, and it may eventually collide with that CO2 molecule, but it doesn't know the difference between that CO2 molecule and the wall of the container over here. They're just hard physical objects that hit each other. So they behave completely independent of each other. There is no attraction between them. CO2 and the other CO2, there's no attraction, there's no repulsion between them. They just fly around like pool balls, and when they hit each other, they bounce off. They just keep on going. Third postulate says that the gas molecules move in a straight line very fast until they hit something. And something is either a wall or another gas molecule. So they fly in straight lines until they hit something. They don't curve, they don't swim in S shapes, and they move fast. And we say that these collisions are perfectly elastic. How many people have taken some physics? You probably dealt with elastic and inelastic collisions. So in the perfectly elastic collision means that when they hit, there is no energy lost. So they behave completely independent of each other, like pool balls, okay? When they hit, basically they keep on moving just how they were. The opposite of that is an inelastic, inelastic collision. That's like when two cars hit each other and get crunched into one, and then they move as one thing. Energy gets transferred from one car over to the other. Fourth postulate. This is what we talked about in terms of pressure. We said that the pressure comes from the particles hitting the outside wall of the container. The particles hit the wall and push it out. So, if we have a small container, the molecules are going to hit the wall more often, right? They're going like this versus a big container. They hit the wall more often in the small container. So that's why if you decrease the volume, you get higher pressures, because you make the molecules hit the walls faster. This also tells us why pressure is proportional to the number of gas molecules. If you add more gas molecules, you're going to get more collisions, and more collisions means more pressure. And I think this is the last one. This is the average kinetic energy of a gas particle. Depends only on the absolute temperature of that sample. Okay? This one is kind of the most often left field of all of them. Okay? You are not going to have to use that equation. Okay? Don't worry about it. We're going to put it up there because we're going to talk to some math about it and how this works out. So this is kinetic energy. Kinetic energy average kinetic energy of the molecules in a sample. That is equal to 1/2 times the mass times the average velocity of those molecules squared. Okay? So what you want to take from that is, if you have a sample that has more mass, is do they have more or less kinetic energy? If you increase m, does KE go up or down? up. If I increase M, that goes up. If I increase V, does KE go up or down? Up. So, if I increase mass, kinetic energy goes up. If I increase velocity, KE goes up. If I increase kinetic energy, this says that the kinetic energy is only dependent on the temperature of your gas. Which means if I just heat up the gas, if I just heat it up, my KE is going to go up. If I have a gas in a sealed container and I heat it up, is the mass in that container going to change? No, I didn't take anything out, I didn't put anything in. The mass is not going to change. So if this changes, 0.5 certainly doesn't change. That's just 0.5. And that doesn't change. Velocity has to change. So if you heat something up, kinetic energy goes up, the velocity, the molecules start moving faster. So gas at a higher temperature moves faster. If molecules are moving faster, they're going to hit the walls more often, and you're going to get higher pressure. Which is why when you heat the gas, the pressure goes up. If you have two different samples of gas, oxygen and CO2, and they are at the same temperature, they have the same kinetic energy. The temperature is telling you the kinetic energy. And so, if oxygen and CO2 have the same kinetic energy, but they have different masses, right? What's heavier, a CO2 molecule or an oxygen molecule? CO2 is heavier, which means that oxygen has to compensate for its low mass by moving faster. If this is lower, that has to be higher in order for the KE to be the same. So lighter molecules move faster at the same temperature. Heavier molecules move slower at the same temperature. So we have three gases here. Which one has the greatest average kinetic energy? How do you find, what determines average kinetic energy? There's something really simple here. If you calculate it, yes, mass and velocity. But there's something even more simple here. No? What did we say is a measure of kinetic energy? What is the fifth postulate that we just talked about? What's the fifth postulate? Absolute temperature. All gases have the same average kinetic energy when at the same temperature. So, they're all at the same temperature. They all have the same average kinetic energy. If you're at the same temperature, you have the same kinetic energy. The masses and the velocities are going to go up and down to compensate for each other so that the kinetic energy stays the same. So, of these, which one has the highest velocity?
H2.
Why H2?
It's
the lightest, right? If it's the lightest, it has to move the fastest, right? Just like if you're a little guy, you better punch pretty hard, right? Or if you're in a demolition derby and you're in a Prius going up against a school bus, you better hit that bus pretty darn hard. Right? So which one Okay. This seems like a unimportant slide. Okay? I'm going to tell you it is a very important slide. Okay? So important that I suggest you look at it multiple times before the most important assignment in this course. If you catch my drift. What is the most important assignment in this course? You said it, not me. Okay? So, all of these gas laws that we've dealt with in the kinetic molecular theory assume that we're dealing with ideal gases. We said this from the very beginning, right? We have the ideal gas law. It's ideal is right in the name. But in real life, our gases aren't ideal. In real life conditions that we deal with, they are so close to ideal that we can't tell the difference between ideal and non-ideal. But when you get into actual gas science, at high temperatures, at high pressures, they don't behave ideally anymore. Okay? So these are the two biggest things that make real gases not ideal gases. When molecules collide, they are not completely elastic collisions. Some energy is lost. Okay? Also, there are attractions and repulsions between gas molecules. We said that they behave completely independent of each other. For the most part, they do. But that's not true by definition. There are attractions and repulsions between molecules, especially at high pressure, when they're really crammed in, and at low temperature. Because think about low temperature, volume goes way down. So your gas molecules get really close to each other again. And when they're close to each other, then they can interact better. If they're far away from each other, they don't even know that each other exists, so they can't have attraction between them. If they're crammed in a tight little space, you get these attractions. So these two things tell us the limitations of our ideal gas laws. Okay? Does that make sense? Circle it. Come back to it. Don't forget it. Okay. So that's the end of that lecture. Let's take a 10-minute break. We'll start at 20 after on that clock, and then we'll do the next liquids and solids lecture. Because you can test it, right? You wouldn't have to do it, but you could. Do you know what glucose is? Oh, you ever heard of Willy Wonka? Movie? It's American. Actually, it's British. You do a Cheeto. Okay.
Yeah, I thought about you while you were gone. And then I found, that's why I put, when you read here, normally answers, you know, and I find out that recipe, I look up to it, then I would get that one. But this time when I ordered the recipe, I get that ready-made back, say, yes, so I think I so I what? Oh, my God.
That's why that one's there.
It wasn't very good. I know, matter of fact, because I have exactly the number, so yeah, someone on my job, so I had to work that first Saturday after you started from the Boy Scout.
That sounds like his boss was not in town, so he had to cut these like extra shifts.
Good. spread apart before after.
At least you wasn't there, so that gave him a little extra, so he had to just sit there and be like, oh, how, cause he missed you, you know, terribly.
Okay, one more. Last one. I don't quite remember this. Looking here, as for, then as a bigger 2 plus.
Beryllium has 4 protons.
Yeah, so I substitute, so 4, 4, 2, because of 2,
So it
right?
starts with 4,
Mm-hmm.
and then it lost to 2,
Mhm.
so it has
2, right, so I pick up that one, 4, 4, 2, right? Okay, for these one, as smallest, I only section energy, so it's from here going up, right? I use these one going up, right? So then I find, so it's that one smallest.
The smallest ionization energy is on the
You
left
look at
bottom
and about the left.
galley.
Is that right? Okay. So for the
Atomic radius
that's
is
go to the left
bottom.
and the bottom's a big go.
Correct.
Yeah, so I'm not very sure whether it's a service like that. I don't go look for something. I said that one. Look at A,
Right.
C, A, L,
The
S, I.
biggest is top or bottom left, and the smallest is top right,
Yeah.
which would be carbon.
So, okay. That was my idea.
So, I had a question for this idea, you know, and then I know how I got this number. However, I'm trying to figure out. And I know that number to use. This 262 was the calorie and heavy work. And then I multiplied that.
Because your specific heat here is joules in it, we had to convert the energy that's big calories, kilocalories, to joules. And so we converted, the conversion between calories and joules is 4.184.
Also, 1 calorie equals 4.184 joules.
Right. And so he did this, in the end, he ended up in the right place. Technically, he had to multiply by 1,000,
Yeah, because you
then multiply by 4.184. But mathematically,
Okay, yeah, what I wanted to ask though is the conversion from calories to joules in the cheat sheet.
it's that metric. It said, let's go.
Yeah, because there was a lot of like kind of conversions you have to go back to that way. I kind of searched up because I didn't remember cheat sheet.
1 calorie, it's 4.1. It also gives you 1 joule and 123 calories. Yeah, so that's a direct conversion from kilocalories to joules. That's not on the cheat sheet. The cheat sheet, you have to go from the kilo, that's big calories to kilocalories. We multiply by 1,000 normal calories, and then multiply by 4.14. But mathematically, that's the same as that. Even 10 to 25, when you cool it. And so, there's 2 ways. There's the math, the long, actually do the problem. But then there's also the opposite. And you get temperature change, and further you get back before you started, you're going to get out exactly how much. And so this number should be the same number.
It doesn't expand.
Yeah, so it's not expanded.
So, and I'm not sure here, because it should be, instead of 10, it should be negative.
They're the same with 2.
That makes sense?
Yep.
Two's at that one.
Yeah, I got it.
I kind of just distract. The reason being, if you can only use the other one instead of Pascal. What is it?
Oh, then the change.
A millimeter of mercury.
No, that's just my, that's one time.
So you convert that to millimeters of mercury, that number goes there too.
So, let's say for this one,
Oh,
I got, it was 0.8001 for 93 point.
Okay, so you got convert kilopascal, then kilopascal,
One thousand.
and then you convert that.
Then how did I convert that?
Well, yeah, I don't know what conversion.
I just had it.
It's old, right, it's 4.18.
You messing with my paperwork, you messing with my homework.
Did I give you that cheat sheet?
Yeah.
Thank you.
I always have it.
And so I don't know which conversion you get the internet, so you're gonna use.
I got that.
But you'll never have to use Pascal or kilopascal.
Yeah.
Oh, yeah, because
That doesn't go a lot.
kilopascal.
For pressure conversion, quiz, or anything, or good. So there is a difference factor between.
It's not really much of a break, huh?
Not having to work.
Oh.
I didn't do much.
I did too.
I had to work extra, yeah.
Me too.
Watch the dogs at home while she was vacation.
Would I multiply 93 times?
Yes, it is.
Because to get my atmosphere, because
She's a
essentially
journalist.
it's not
Sitting here.
I was telling her, I said, well, they get ready to look at this time. They work it in till you die.
Yeah. The work always makes it, it's time. It's work in the gym, out and about with dogs, 8 days to feel like.
Other way to do it is what is you think?
As long as
Yes, I can imagine.
it gets work done sometimes.
One atmosphere.
What happens? Gonna take 101.
One atmosphere.
So if you're converting kilopascals to atmosphere, that number where it gets bigger. If I'm converting kilopascals to atmosphere, you're not using a bigger measure. It's like if you haven't been.
I'm just gonna say it's like.
Say there's not much.
It shouldn't take that
Number
much.
can be wrong.
Oh, yeah.
Somebody got me on
In this case, so like in this case, we're using kilopascals, which are smaller.
Right. So you make the number, make your conversion small. So multiply by 101, divided by 101.
Also, instead of multiplying, divide. So in this case,
Kilopascals
divided by that, and it gave me that almost kilopascal, but not quite. And then that's when I
You don't like the way it looks?
do the conversion.
You know how many atmospheres,
I know, you know.
Yeah.
I guess that's the way it looks.
and then you convert it with the core millimeters of mercury, convert to millimeters to inches. And then this is another one. Your calculation numbers.
Okay.
So you have to agree that I, in this
The second one is correction of
Okay, we're gonna move on. So we finished our gases. Gases took a lot of time. Liquids and solids have 21 slides, and this is one of them. So this is gonna be a whole lot quicker. So, you know liquids and solids. What is the difference in properties between solids and liquids?
Solids have a definite shape.
Solids have a definite shape? Do liquids have a definite shape?
No.
No. Do solids have a definite volume?
Yes.
Yes. Do liquids have a definite volume?
Yes.
Yes. And so because that volume doesn't change, all of those gas laws are gone. Boom. There are no equations for solids and liquids. Okay? So that's the properties on our level. Okay? I think the very first week of class we talked about how they're different on the molecular level also. How are solids and liquids different at the molecular level?
Solids, the molecules are more condensed.
In the solid, the molecules are more condensed. And there was another thing that we talked about in terms of, remember? What about their speed?
Liquid moves faster.
Liquid moves faster, right? Solid basically doesn't move at all. They just kind of shake in place. And the liquid moves a little bit. They move a little bit, but they don't move very far, and the gases move all over the place. So, which is a liquid cat and which is a solid cat?
The first one,
First one is what?
a liquid cat.
First,
Well, he's in a bowl.
Can't move, neither are these solids.
Ah, I see.
well, that's not, I look at it as he's
That's-
taking the shape of the container.
Yeah, so he's essentially a liquid, right?
Yeah, that's a liquid cat.
Yeah.
And then that one's stiff. That's a solid cat.
Yeah, I didn't see that.
Everybody always likes that one. So you know that if you put a liquid out on the bench, or on the desk, on the table, over time it's going to evaporate, right? Even if you don't heat it, it may take a long time, but it's slowly going to evaporate. And so we say that liquids and gases are at equilibrium. Have we used the word equilibrium yet? So an equilibrium means that there are two processes that go in opposite directions. So this is saying that liquid goes to gas, and at the same exact time, gas is coming back to liquid. That's an equilibrium. They're both happening at the same time. And it's an equilibrium, only a true equilibrium if both processes, that one and that one, are happening at the same speed. If the process of liquid to gas is happening faster than the process of gas coming back to liquid, overall, our sample is going to appear to go from liquid to gas. But if they're happening at the same exact speed, the amount of liquid that we have and the amount of gas that we have to our eyes will never change. Okay? So this is a little flask here. We got a stopper at the top. We have some water down here. And then we have empty space. We put that water in there. Slowly, that water is going to evaporate, right? And it's going to evaporate, and you're going to get water vapor. And so, at some point, one water molecule breaks away. So one water molecule went that way. And then a second one broke away. And a third one, and then a fourth one. But these are gas molecules. They fly around. If a gas molecule flies around and it hits the water at the bottom, it's going to stick to the water. And so you have them flying around up here. that one is about to fly into the water. So when it hits, we're going to go back from gas to liquid. And the more gas that you have up here, the more often one of them is going to hit the water and stick. And so the water is going to evaporate until you reach an equilibrium where they are hitting at the same speed that they're coming out. And that is the true equilibrium between the liquid and the gas state. And the pressure that you measure up here, when it's at that equilibrium, is called the vapor pressure. So that is the pressure that a liquid wants to make above itself. And so let's say the vapor pressure of, I don't remember the vapor pressure of water at room temperature, but let's say it's 10, let's say it's 2 atmospheres. Okay, let's say it's 2 atmospheres. That water is going to evaporate until it makes 2 atmospheres up here. And when it makes 2 atmospheres up here, then it's going to be going down and up at the same rate. This is very, very similar to boiling. The only difference is here, we're doing it at a low temperature. It's happening very slowly, right? Only some of the molecules are going from the liquid to the gas at any given time. If you are boiling something, it is going from the liquid to the gas very, very quickly. And they're all trying to go at the same time. The boiling point is the temperature where the vapor pressure equals the atmospheric pressure. That's a kind of a complicated definition. I wouldn't worry too much about it at this point. Okay? But let's look at our water curve now. This is a vapor pressure curve. We have atmospheres over here. We have degrees Celsius over here. Okay? So we have a sample of water and we're going to heat it. If you heat water, is it more or less likely to evaporate? It's more likely. And so when you heat something, when you heat a liquid, its vapor pressure goes up. It more wants to be in the gas state. So when we heat it, we go this way, the vapor pressure is going to go up. And we've drawn this 1 atmosphere line here. 1 atmosphere is atmospheric pressure. So when the vapor pressure curve of water crosses that line, that's the boiling point of water. So we go until we hit the line, and then we go down, and what do you know? It's at 100. Okay? So this is methanol. What is boiling point of methanol? I guess that's 20, 40, 60, 80, 100. So it's a little over, take that line, so it's a little past this vertical line. So it's a little over 60. This is methane. I guess that's negative 120, 140, 160. It's a big difference there, right? Negative 160 versus 60 and 100. So one of the things we're gonna look at is what makes these big differences. And what makes those differences is the attractions and the repulsions between molecules. We just said that in an ideal gas, they aren't there. In a true real-life gas, under certain circumstances, there are attractions and repulsions between gas molecules. In solids and liquids, they are always there. That is what we study in the solids and the liquids. Those forces between the molecules. And we call them intermolecular forces. Inter means between molecules. From one molecule to a next. Not intramolecular forces, which would be bonds. Okay? Ionic covalent bonds. Those would be intramolecular forces. These are intermolecular forces. So we can use these to answer questions. At room temperature, water is a liquid, right? At room temperature, CO2 is a gas. CO2 is out here. Why? Without having talked about intermolecular forces yet, do you think that the intermolecular forces holding molecules together is stronger in the CO2 or the water?
The water.
Why the water?
Because of the state.
Because it's a liquid, right? And so if the water is a liquid, the molecules must be closer. And so there must be a reason that they're closer. There's something holding them together. Whereas the CO2, they're out here. There's nothing holding them together. So the intermolecular forces of attraction are higher in that water. That also tells us why different liquids have different boiling points. Let's come back here. Let's look at water and methane. Water has a much higher boiling point than methane. Which one do you think has the greater intermolecular forces holding the molecules together? I heard both. Who says water? Who says methane? Who wants to explain their answer?
I thought water because it takes more heat to get it to change. So it takes more to get it to change, so it's.
Right. And so when you're boiling something, what you're doing is you are putting heat into it in order to pull the molecules apart. When you add heat, you're raising the temperature, you're increasing their kinetic energy, you're making them move faster. The boiling point is the point at where you make them move fast enough that they break away. And so if you have a very high boiling point, that means you have to put a lot of energy into it in order to pull them apart. Methane takes basically nothing to pull them apart. Liquids actually tend to stick together. You think of Elmer's glue. Even when it's not hard, it's still sticky, right? Elmer's glue is a liquid. Liquid molecules stick together. Okay, that's capillary. Have you ever heard of capillary action? If you put it works best in little tiny tubes, capillaries, little tiny tubes. And if you ever put a straw in a glass of water, what is the water level in the straw versus the water level outside the straw? Have you ever noticed?
It goes up when.
It goes up. The water level in the straw is actually a little bit higher than the water level in the glass. It seems strange, but that's because the water molecules are sticking to the straw and trying to climb up the straw, and when they climb up, they pull other water molecules behind them. And so you get a little extra raise up. This is actually also how plants move things in their I don't want to say bodies, I'm not sure what the right term is. But if we need to move nutrients from my foot to my hand, how does my body get it from my foot to my hand? My blood. I have a heart that pumps the blood around, right? A tree does not have a heart to pump sap around. So what they do is all the nutrients in the ground, right? They come into the roots. They need to get up to the tip of that tree. The tree has capillaries that take the water from the ground up to the top of the tree. The water pulls the nutrients up with it. When the water evaporates off the top of the tree, imagine you have a little chain. You have a little chain of water molecules inside this capillary. When you get to the top, and this one flies out, everything underneath moves up a spot. And so you have this constant flow of water coming in at the bottom of the tree, at the roots, coming up, and out at the top. So you have this constant water flow, and so it moves the nutrients from the bottom to the top, and it only works Because that water molecule is stuck to that one, which is stuck to that one, and that one, and that one, and that one, and that one. If you break that chain, if the water molecules all of a sudden decide, I'm not going to stick to the next one, that's going to die. Liquid molecules stick together. There are three types of forces that we're going to talk about between molecules. Each one we're going to talk about in depth, but we have London dispersion forces, dipole-dipole forces, and hydrogen bonds. London dispersion forces are the most complicated of the three. Okay? These are two atoms. Okay? In the center, we have the nuclei, and then we have the electron cloud around them. Until now, we have always drawn our electron clouds as spheres. On average, over time, they are spheres. But electrons move randomly. And so at a given, in an instant point in time, it is possible that there may be more electrons on one side than the other. And so in this picture, we have more electrons on this side. See how it bulges out there? And so we have more electrons on that side of the molecule than we have on that side of the molecule. And if we make it a little more extreme, we have even more over here. And if there's more over here, that means we're losing them from over here. And you get more and more extreme. And it gets to the point that we have so many more electrons over here compared to over here that we get partial charges. We get a partial negative over here and a partial positive over here. So in a single atom, we didn't gain electrons, we didn't lose electrons, we don't have actual charges. But at one infinitesimally small amount of time, there was a positive, partial positive, and a partial negative. 1 picosecond later, it could be back there, it could be here, it could be flipped the other way. But for that one point in time, we had partial forces. And if they both did the same thing, and they did them next to each other, we now have a partial negative next to a partial positive. Opposites attract. These two atoms are now attracted to each other. Even though they are two neutral atoms that would normally seem to have no reason to be attracted to each other, at that one instantaneous point in time, there was attraction between them. But because a sample of something has so many atoms in it, remember a mole is 6.022 times 10 to the 23rd. That's a lot. Just by sheer odds, there are quite a few molecules that happen to line up like that. And so there is actually a measurable attraction between them. Okay? If this doesn't, the electrons moving randomly doesn't make sense, we'll see if this does. Does anybody have a small furry rodent pet? A small furry rodent pet. Have you ever had one?
Like a hamster.
Like a hamster, okay? Yeah. Imagine you had a container with 100 hamsters in it, okay? And those hamsters were negatively charged, okay? And we dump them in the middle of the room. They're going to run around randomly, right? If I take a picture, it's possible there may be 60 of them over here and 40 of them over here. At that point in time, we would have more negatives over here than over there. The next picture, there might be 100 over here and 0 over there. They're moving randomly. These charges change constantly. But at one point in time, they're not going to be spread equally. The odds of the hamsters being spread perfectly equally amongst the center of that room are basically 0, right? But if you take a long period of time and average it all out, they're going to be average that they're all right in the middle of the room. That's the same thing we're dealing with here. If we take a time scale that we can see, an atom looks like that. But if we take a split second, an atom actually looks like that. It may be skewed up, or may be skewed down, or to the left, or the right, or in, or out. And it's changing faster than we can even comprehend. But it is there, and there are attractive forces between them. So, because this is due to electron clouds, which molecules, which elements, which atoms have electron clouds? Let me ask this question. Which atoms, molecules, or elements do not have electron clouds? Any of them? No. Everything has electrons. If you have electrons, you have electron clouds. If you have electron clouds, you have London dispersion forces. So every single liquid has London dispersion forces. There are no exceptions. If you have a non-polar substance, the only intermolecular force you're going to have are London dispersion forces. The other two will not apply to non-polar substances. But if you have a polar substance, you will still have London dispersion forces. The strength of these attractions is based on the size of the electron cloud. A bigger electron cloud can get more distorted, right? If I have 100 hamsters, the most distorted I can get is 100 and 0. If I have 200 hamsters, I can get 200 and 0. That's a bigger distortion. And so, the more electrons you have, the stronger these forces are. And you can figure out how many electrons you have just by the mass. If you have a bigger element, you're going to have more electrons. And so, if we just look at our three halogens, chlorine, bromine, and iodine, which one is heaviest? Chlorine, bromine, or iodine? Iodine. Iodine is heaviest, so it has the most electrons, so it would be the most distorted, and so you would have stronger forces holding the iodine molecules together. If we look at room temperature, chlorine's a gas, chlorine's the lightest, iodine's a solid. The forces are so strong that they're actually holding the iodine molecules together in the solid state. So heavier molecules have stronger London dispersion forces. So if you're given a question that says, which one of these has the largest London dispersion forces, all you have to do is calculate the molecular weight of each one, and whichever one gives you the largest number has the strongest forces. Okay? That's all there is to it. So, helium or krypton, which one has stronger London dispersion force? We've got helium and krypton. Krypton. Krypton's heavier, stronger forces. What about HCl or HBr?
HBr.
HBr, because the bromine part is heavier than the chlorine part over here. So HBr is bigger than HCl. What about CH4 or C2H6?
C2H6.
C2H6. That's the extent of that. CH4 or SiH4?
Yes, I.
SiH4, because Si is heavier than the carbon. And then there's 4 hydrogens involved. That's London dispersion forces. Next one are dipole-dipole forces. So we said London dispersion forces were because of those temporary distortions that cause partial positives and partial negatives. But we've already talked about partial positives and partial negatives in polar molecules. In polar molecules like this, these are permanent. It is always partial negative, and it is always partial positive. Which means that if it's permanent, that attraction always exists. And not only does it always exist, it exists between every single molecule in your sample. And so, it adds up a whole lot more. Because at any given point in time, they are all attracted to each other, versus with the London dispersion forces, only some of them are. So dipole-dipole forces are in polar molecules, and they are stronger than London dispersion forces. So they're called dipole-dipole because these partial positive, partial negatives, that's called a dipole. And so if you have one next to another, it's a dipole, so you get a dipole-dipole force. This is SO2, sulfur dioxide. We got sulfur with a partial positive, the oxygen's over here with a partial negative. And so if you put two next to each other, this partial positive is attracted to this partial negative, and they want to hold the two molecules together. But not only do we have the dipole-dipole, we still have the London going on at the same time. Because this is our new starting point, but it can actually get further distorted from that based on the random movement. So we can get even stronger negative and stronger positive. So, does this experience dipole-dipole forces? Yes. Why? Say it again. What type of molecules did we say have dipole-dipole forces? Polar. Polar. So what you're looking at, is it polar? And this, answering the question, is it polar, I realize is one of your least favorite things to do. But, is that molecule polar? Yes. It is not symmetrical, right? The red ones are over here, the yellow ones over there. If it is polar, it has dipole. Does that have dipole-dipole forces? Yes, it is not symmetrical. Does that have dipole-dipole? Those green ones are pointing down a little bit. Yes. You have green ones on the bottom, nothing up top. In this one, the three yellow ones are evenly spread around the center of it. No. This is symmetrical. This is one of those hard ones to see that it's symmetrical, but they're spread equally around the center. They cancel each other out. That is not a polar molecule. It does not have dipole-dipole forces. Which ones have London forces? All of them. If it exists, it has London forces. When you think about polar bonds, polar covalent bonds, and ionic bonds, an ionic bond is really just a completely polar bond. To the point that it's not a partial positive and a partial negative. The electron is completely moved over. It is a complete positive and a complete negative. So ionic compounds have very, very strong dipole forces. Because the charge differences are very, very high. Which is why ionic compounds have very high melting temperatures. If you're going to melt an ionic compound, that means you're going to move the molecules a little bit apart from each other. And to do that, you're going to have to overcome the forces holding them together. And if they have very strong dipole forces, that's going to take a lot of energy to get that to break and melt. And so, if you have a larger charge difference, that is going to mean you have a stronger force between them. This is just for ionic compounds, okay? So, which one of these two ionic compounds has the stronger dipole forces between magnesium oxide or sodium chloride? What you want to do is figure out the difference in charge between the magnesium and the oxygen, and the difference in charge between the sodium and the chlorine, and figure out which compound has a bigger difference spread between them. So, what is the charge on my magnesium? 2 plus. That's my charge in the oxygen. 2 negative. Sodium is chlorine's negative. Which compound has atoms or ions that are further apart from each other in terms of charge?
Mag and ox.
You got 2 plus and 2 minus. That's 4 apart. Did you see that?
Yeah.
So if you have a number line, that's 0, -1, -2, 1, 2, 1, 2, 3, 4. They're 4 apart. Here, they're 2 apart. So a larger charge difference means a stronger force. Put a star next to that. You're going to need that sometime later on in the future. The third type of force is hydrogen bonding. If you look at boiling points of a large number of liquids, you're going to see a trend based on molecule size. The heavier it is, the higher the boiling point. You're going to see trends based on dipole forces. And then all of a sudden, out of nowhere, you'll see a molecule that has this incredibly high boiling point for no good reason. It's a little molecule, it has basically no dipole forces. There should be more or less nothing holding it together. But it has a really high boiling point. Water is an example of that. Water is a small molecule, it's very small, 18. Oxygen and hydrogen, that's not a very strong dipole. So why does it take so much energy to boil water? It's because of hydrogen bonding. Hydrogen bonding only occurs in molecules that have hydrogen covalently bonded to nitrogen, oxygen, or fluorine. You have an NH bond, an OH bond, or an FH bond. Hydrogen bonded to anything else will not cause hydrogen bonding. If you're looking for hydrogen bonding, you have to have hydrogen on a nitrogen, an oxygen, or a fluorine. So if you see one of these outliers in a boiling point table, if you look at it, it probably has one of these in it. You have hydrogen bonding going on. So in hydrogen bonding, what we basically have going on is molecules that are sharing hydrogens. So we said that covalent bonds are sharing electrons, right? In hydrogen bonding, the hydrogens actually partially come off of one molecule and get shared with another one. And so here, that hydrogen is being, in a sense, shared with that oxygen. That one's being shared with that one. But at the same time, that oxygen that's losing these hydrogens are sharing these. And so what happens is you have this big mess where all of the atoms, all the molecules, are sharing with each other, and nobody wants to leave, because if they leave, they're going to end up on the short end of the stick, and they're not going to get all their hydrogen back. And so that forms a very strong bond between them. Same thing happens with ammonia in water. Water has oxygen hydrogen, ammonia has nitrogen hydrogen. So it doesn't have to be oxygen hydrogen with oxygen hydrogen, you can mix them. Nitrogen hydrogen with oxygen hydrogen, ammonia will hydrogen bond with more ammonia. Hydrogen fluoride, HF, will hydrogen bond with itself. It would hydrogen bond with water. It would hydrogen bond with ammonia. hydrogen bonds are what hold together DNA. That's because hydrogen bonds are strong. They're very strong. They can hold the DNA together, but they're also reversible. You don't have to break a bond to pull apart a hydrogen bond. You just have to pull hard enough, and it'll go back, the hydrogens will go back to where they're supposed to be, and the molecules will move on with their lives, okay? So why do you need to be able to break DNA? Breaking DNA seems like a bad thing. Somebody's taken biology. Well, cloning, but let's just say it again.
It goes into RNA.
It goes into RNA, right? DNA is used to make RNA. And when you make RNA from DNA, you have to pull that apart. You only use one strand of DNA at a time. So you have to be able to pull that DNA apart in order to make the RNA. Not only that, when the cell divides, it has to double its DNA. And you replicate one strand at a time. So you need to be able to pull that DNA apart whenever you need to and put it back together. And so it's like, I can't even think, it's like Velcro. It's a pretty good stick-em, but you can pull it apart and put it right back, right? If you use glue, it's gonna hold really well, but once you pull it apart, it's toast. But if you use, I don't know, what's something that holds not very well? Nobody's got anything yet. Static electricity. That's not going to hold things together very well, right? And so in DNA, we have these hydrogen bonds forming, and so there are four different bases, right? In DNA is adenine, thymine, guanine, and cytosine. And cytosine bonds to guanine. So these each have 2 hydrogen bonds. And so that's why the C's and the G's always bond together. If you put DNA together, the C's will always be opposite the G's, and the A's will always be opposite the T's. It's because the C's and the G's have 2 hydrogen bonds each, and the A's and the T's have 3. So, will that molecule have hydrogen bonding?
Yes.
Yes. It has nitrogen bonded to a hydrogen. Will that have hydrogen bonding?
Yes.
No,
No.
it doesn't have hydrogen.
It doesn't even have hydrogen in it. What about that one?
Yes.
You gotta be careful where the hydrogens are. The hydrogen has to actually be on the oxygen. So this molecule has an oxygen, it has hydrogens, but none of the hydrogens are on the oxygen. So that will not have hydrogen bonding. What about that one?
Yes.
Yes. That hydrogen is on that oxygen. What about HCl? No. Okay. So, if you have hydrogen bonding, you also have London dispersion forces, right? If you have dipole-dipole forces, you also have London forces. And so if you look at all molecules in the universe, all going to have London forces, every single one of them. And then a subset of them, polar ones, are going to have dipole-dipole forces. And then a subset of those are going to have hydrogen bonds. We've got 3 types. You need to be able to figure out, when I give you a molecule, does it have hydrogen bonding? Does it have dipole-dipole forces? Does it have London dispersion forces? So, here's another way we can look at these problems. If we have 2 molecules, carbon monoxide and HF, which one has the strongest intermolecular forces? The way to figure that out is to figure out which types of forces each one has. Do either of them have London forces? Yes, everything has London forces. Do either of them have dipole forces? Are either of them polar? Yes. They are both very polar. To be polar, you have to have two atoms bonded together that are not the same element, and then they can't cancel each other out. Are carbon and oxygen the same element? No. Are hydrogen and fluorine the same element? No. They are polar. Okay. So if they're polar, they have dipole forces. And so if they both have London, they both have dipole, we haven't figured out yet which one is stronger. Does one of them have hydrogen bonding going on? Yes. Which one? HF. So HF has hydrogen bonding, dipole, and London. This one only has London and dipole. So HF has the strongest intermolecular forces. Which one would you say has the higher melting point? Why?
Because you said if it's harder
Right.
to boil, it's going to be stronger.
Correct. In order to make it melt or to make it boil, you're pulling the molecules apart. And the stronger the attractive forces, the harder it is to pull them apart. And so HF has stronger forces, so you're going to have to heat it higher in order to get it to melt or boil. So, which of these two should have the highest boiling point? Which is also asking which one has the strongest forces. Why? Has hydrogen bonding, right? This one is actually heavier, right? The sulfur is heavier than oxygen. This one's heavier. And so this one has stronger London than that one. They're both going to have dipole, but that one is hydrogen. And hydrogen trumps everything. Hydrogen bonding immediately takes you to the top. What about this? Which one has the strongest forces?
CAS?
Why? Has dipole. This is non-polar. It's phosphorus bonded to phosphorus. It is non-polar, only has London. Here we have London and dipole. What about here? First one. This is only London, London, and dipole. Okay. So, what you need to take from this is in terms of London dispersion forces, the larger molecules have a stronger force. For dipoles, a larger charge difference equals a stronger force. Hydrogen bonds exist in molecules that have an OH, an NH, or an HF. Okay? I think this last slide, yes. So, in the homework, on quizzes, on the final exam, you're going to struggle with things, and you're going to think we didn't go over them. Okay? And I'm going to tell you, look at the last slide of the lecture. Ignore the first 20 of them. Look at the last slide, and the question you're asking me is going to be answered on this slide. Okay? If you still don't get it, certainly email me. But look at this slide before you email me. Okay? Questions? Okay. Let's go over the homework.
So that be that answer, or will you put the two together?
That will be it, because only three, that's 3 sig factor.
So I need to convert 210 calories to kilojoules.